Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Aero 3261, Lecture 20 on Oblique, 3D, and Principal Stresses. We can start by reviewing our understanding of stress tensors. Now, I introduced this at the earliest part of this class, where we saw that a stress tensor enabled us to describe the stress completely because it has both force information and area information. Forces perpendicular to the area are normal, cause normal stresses, and cause stress against the perpendicular area. Forces that are parallel to an area cause shear stresses in that area. And we know that the romantic nature of the shear stresses causes them to be head-to-head, tail-to-tail. And the antisocial nature of the normal stresses cause the reactions to be opposing at all times. We also previously took a look at stress tensors in the simplest manner. Remember, this is a stress on the x area in the x direction. That means it's a stress that acts on the area that's perpendicular to the x-axis in the direction of the x-axis. This is the stress acting on the y area, or the area that's perpendicular to the y-axis in the y direction. This is on the z-axis in the z direction. This is on the x area in the z direction, on the x area in the y direction, and so on. Looks like we have a typo down here. This should be on the z face in the y direction, as we see, and this one's on the y in the z direction, so the upper one is correct and this one to the left incorrect. Now, just to review also, we also did all of this where we saw that normal strains were the deflection over the original length, and on a little element dx, that would be the change in length dx over dx. The strain in the 2 direction is the change in y over y. The strain in the 3 direction, the change in z over z. Shear strains, once again, on the 2-3 face would be the change in the y relative to z, and the change in z relative to y. Remember, because we're talking about the summation of those two strains, which is the total strain in the element, recalling back to our first, that was around our 3rd-ish lecture or something like that, 4th lecture. We also learned about Poisson's ratio. Since the strain is still simply stress over modulus, and although we have no stress on the perpendicular faces in this axial load case, we saw that we got a strain that is proportional to the normal strains based on Poisson's ratio. So all of these are old topics that we need to have at the forefront of our mind, as also is the following one, where here we looked further into the strains and we saw that if we have stresses in all 3 directions. Now the difference is, last slide we saw only stress in one direction. Now we have stress potentially in all 3 directions. And in the x direction, the strain will be just the stress over modulus for that direction. But it will also have a little effect due to the other 2 stresses. We should have mastered this before. What this means is, if we have an element, and if we have a stress in this direction, then our strain is simply the strain in this x direction is simply stress over modulus. So that is how much strain we're going to get, or change in length with respect to length. That's the total strain in the part for a uniaxial load. But if we have, so that load caused a little lengthening like this. If we have a stress, this was a stress in the x direction. If we have a stress in the y direction, what that means is this is going to cause a strain in this direction. But we're not talking about that, because what we're seeing is as it grows in this direction, it also gets narrower in that x direction. So that strain in the x direction, the strain in the x direction due to this guy, is going to be its stress over modulus times Poisson's ratio, but it's negative. So the negative of Poisson's ratio times its stress over E will tell how much strain it causes. So it's actually causing a little resistive strain. If we also had a stress in the z direction, then that stress will cause a strain equals to its stress over modulus Poisson's ratio negative. So what we see here is it's the summation of the stress that's normal and the two transverse stresses, which gives us a strain in the normal direction, 3 components of strain in the normal direction, the total of which is the total strain in the x. And correspondingly for the y strain and the z strain is going to be a combination of how much that part lengthens due to the one load and how much it narrows due to the other load and the other load. So these are old topics, but if we don't understand these, where we head today will not make any sense. So having understood those things, we're ready to look at oblique stresses. So let's take a look. If we just have an element loaded in tension, we know the stress is P over A. That's talking about the stress, the average stress on an area cut perpendicular to the force. Yet this stress is three-dimensional, and if we make a different cut, we will get a different resultant. Now we could still talk about the stress in that x direction, but really we have no allowables for stresses that are skewed to the plane of the area. All we have is allowables for stresses that are perpendicular to the area, which we call normal stresses, or parallel to the area, and these are called shear stresses. Therefore, if we make any cut other than a perpendicular cut, if we find that the force is not perpendicular or parallel to the area, then we will need to resolve that force into components, normal and parallel to the area, so that we can evaluate what the shear stress and the normal stresses are and assess whether we're okay. So let's say we cut a plane at some angle from the vertical axis. Now we moved away from this round part we started with and we went to a square part to make things simpler. If we cut any other plane, we still have the same action-reaction pairs, P and the reaction to P. But at that plane, while we still know that the total stress in the x direction is P, we can resolve it into its components that are parallel and perpendicular to the area. That means the force will change, and we can evaluate the change based on simple trig. However, the area also changes. If you look at that length, which was b, the width of the part, it now becomes b prime, and that b prime dimension is also a trigonometric function, or can be determined with a trigonometric function. We know that originally we had stress equals P over A, and the area was BT. And for our cut plane now, since our B is now B prime cosine theta, it's easier for most of us to think, hey, B prime equals B, or if B prime is our hypotenuse, then B is just B prime cosine theta. So that means that B prime is simply B over cosine theta. So our area on the angled on the angled plane is just b prime t, which is bt over cosine theta. Okay. And our force now has these components, p cosine theta, p sine theta. Great. So our new stresses that are normal and shear to the plane, or normal, parallel and perpendicular to the plane, are now the normal force over the area and the shear force over the area, which becomes these two relations. Now we can write these as a function of our original P over A stress for the original force by just plugging in sigma for P over BT anywhere we see that. And that gives us this form of the equations. Now this starts to look like hocus pocus when we look at the sigma on the theta plane and the tau on the theta plane. But really all it was is simple trig resolving our force into normal and parallel components and our area into the proper rotated values. Now if we look down here at this little graph, we see that we're plotting the stress against our angle. So if we have a cut, if our angle is 0, we would expect to see the entire sigma that we started with, P over A, and if our cut is 90 degrees to that, we should expect to see our stress to be 0, as we see on this particular slide at these 2 points here and here. However, shear stresses and normal stresses have a different magnitude, and so in order to show them on the same graph most in a fashion that's easiest to understand, we're going to go ahead and take whatever the stress is, and we're going to divide it by that original stress. So the stress on the inclined plane divided by that original stress that we calculated back here, P over A, or actually back here. And in the same way, we're going to take that shear stress on that inclined plane and divide it by sigma. That's what we're seeing here. We're plotting on this vertical axis that normalized stress. So since we're normalizing against that perpendicular stress, actually, if we cut a plane like this, perpendicular to this force, then we would expect the stress to be exactly what we saw originally, and so our thing is 1. If we actually cut a plane that's parallel to our force, we would have no normal stress at all. And we see that it changes in a trigonometric fashion between. Now if we make a cut perpendicular, we're going to expect no shear stress. But what we're going to find is as we cut a larger and larger angle, we're going to get more and more shear stress until we pass 45 degrees, and then our shear stress is going to diminish. So our shear stress on the element is going to go from a 0 to our shear stress on the element. So our shear stress on the element is going to go from 0 to a maximum value and back down. The maximum is going to occur at 45 degrees, and the magnitude is going to be 1/2 of the normal stress. So this gives us some interesting relations that our shear stress at some angle, if we cut different angles, it's going to change, which means our little element under stress is changing, and our shear stress will go from 0 to a maximum value of half the normal stress and back down to 0. So we should be able to, the first thing we're going to need to be able to do is to resolve our stresses into normal and perpendicular components into normal and shear stresses, basically. And this is the kind of small thing that we will do. We should be able to still use trig and do this kind of thing. Now let's imagine that we have a plate and like this one, and we have loads on the faces. This is called plane stress because actually one face is unloaded. This is like, let's say we have a skin where we have a continuous piece, and so imagine we have our fuselage and we take one little element out of that and focus on it and draw it like this. We might have stresses in this direction, which we can show this way, which with action-reaction pairs. That would be the x direction, in the y direction, we might also have a state of stress. Now we're going to pretend that this is a little plane stress element, which means there's actually no stress normal to the face, which is very common in thin-walled structures. Since there's nowhere for that load to go, we're going to say that that's unloaded. The stress is zero in that direction. We might also have shear stresses on that little element. And if we draw the little element, what that means is in the x direction, we're going to have normal stress. We're going to have stress in the y direction. We're going to have shear stresses. And that will be, and this other z face is unloaded. So this is showing the complete stress state on that element. These are shear stresses. Now, what we have to be careful of is when we talk about sign convention for stresses, for shear stresses, normal stresses, our sign convention is going to generally be always positive for tension and negative for compression. Shear stresses, remember when we had a beam, then we called it positive. We were chopping off the beam. A beam, positive, was chopping off the beam moving from left to right. And we will still use that nomenclature for any kind of beam-like things, but when we're talking about shear elements, we usually call a positive shear stress on a little shear element that's not chopping off a beam positive in this orientation. Really either one, and this is a tau here. So this is sigma x, sigma y, and tau. And if we draw tau anywhere, since these are the same, these are the same, then that means we know what all these taus are, right? On every face, they got to be the same. So you got to be alert to the sign convention for shears. Usually we're going to call this sign convention positive for a little shear element, while we're still going to use this chopping off the beam positive for a beam element. Okay, you're going to have to be alert and not miss that. Now, sign convention is going to be critical because we're going to be learning to transform our stresses today, and so if we have the sign in the wrong direction, that's going to mess everything up. We already said that. We said this. Isolate a little element. Once again, we're seeing this positive sign convention means it moving up. Now, if we had cut any other plane for our stress, once again, we're talking about this little element here, but if instead, if we cut the element here across here with an element like this, then actually this stress is going to change into two components, and this stress is going to change into two components, and the summation of those is the total stress on the part. Once again, as we saw in the prior slide, these are going to be a function of trig, but now we actually have 1, 2, 3, 4 stresses that all are feeding in to what that resultant normal and shear stress is on that face. And the way this is showing it is by cutting this element here. This is showing the cut with some angle theta, which we're seeing here, what those resultant stresses are. Those resultant stresses are going to be a function of both the normal stress in the x, the normal stress in the y, the shear stress on both faces. And fortunately, it resolves to a nice simple equation. This is our plane stress transformation equation. When we have an element like this that's under plane strain that has sigma x and sigma y, and it has shear stresses, with this being the positive, then you will plug in the sigma x, the sigma y, and the tau into these two equations, and that will tell you for any rotation theta of that element, which means let's say we rotated it by theta from the horizontal, that will tell you what the normal stress and the shear stress is on that face. Now, because these are action-reaction pairs, if we plug in this theta, we're going to get this normal and shear stress, and if we plug in that theta plus 180 degrees, we're going to get the exact equal and opposite stresses, or else something's wrong. Make sense? Now if we do this, we're going to find that as we rotate this element, we're going to get our normal stress on each face is going to change and our shear stress is going to change. Now we started off with an element like this. We had a normal stress and a shear stress, but we also had normal stress and shear stresses over here. As we rotate the element, the stress in this theta direction is going to change, as will the shear in the theta direction, and we're going to find that the stress in the 90 degrees to the theta is going to change, as will its shear stress. Both of these change. And if we focus on the stress on the face we're looking at, that's what's given by this equation here. So we're going to find, as we take this element, imagine it's spinning this way about the center. If we spin that element under a given set of forces, we're going to find the normal stress change from one value to another value and back again. That means it's going to change in magnitude up and down. At some point, that normal stress will be maximum. And at some point, the shear stress will be maximum. And these will not be maximum at the same point. We're going to find that the maximum stresses can be determined by a variant of this equation that finds the maximum values. The maximum values are called the principal stresses. The principal stresses. My dad was a principal for a lot of years. These are his stresses. So you should send him a check whenever you calculate them. No, just kidding. You got that? So this equation will transform our stresses for any rotation of the element. We're going to find a different equation that will identify these maximum stresses, and that's what we're going to study. There's a lot of work done around the principal stresses when we have elements like this one up here that has stresses on multiple faces. Now, as you think back to calculus, if you differentiate the equation, you can find out at what value it's maximum, and we find that the maximum values are going to occur at the principal angles. We could call them phi p and phi s. You'll notice I talked about this being theta before. Actually, this nomenclature is phi. The nomenclature we started with up in Shanley's picture was theta, and in Shigley's picture it's phi. So if we talk about that angle of the element, phi, then there's going to be an angle at which the normal stress is maximum and an angle at which the shear stress is maximum. Okay? And these are those two angles. If we plug those back into our stress transformation equation, we get the equation for the principal, normal, and shear stresses. Now you'll notice this looks like two equations, but it's really one equation that plays out four ways. Okay? Let's think about that a minute. These equations, remember, these equations give us the stress on any face for any rotation, phi, this angle that I called theta before. We're calling it phi in these equations. Okay? So what this means is if we figure out what those, by differentiating, we find that the angles where they're going to be maximum are these two angles. And if we plug those back into these equations and do some algebraic manipulation, we're going to get these two equations down here, the two principal equations. You'll notice this is really one equation right here. One equation. It's going to give you both stresses, sigma 1 and sigma 2. Okay? Sigma 1 and sigma 2. That means when we have rotated this element, we're no longer going to call it x and y, because that was our original coordinate system. We're going to call it sigma 1 and sigma 2 on those two faces now. Okay? So the stress in the 1 and the stress in the 2, which is actually at some angle which we're calling phi. Okay? So the way we get it, we can just plug in our x stress here and here. We can plug in our y stress here and here. We can plug in our shear stress right here. That was a shear stress on that original face. Whatever this value is, whatever this value is, whatever this value is. We don't need to plug in both these values because they're the same, remember? So we plug in this, this, and this. sigma x, sigma y, and tau xy. Tau on the x face in the y direction, which is the same as tau on the y face in the x direction. Okay. Plug in those three values. Then we're going to actually get two values because we have a plus and a minus. We're going to get one value and another value. One value is going to be maximum. The other one is going to be the alternate value. So this is the max stress sigma 1, and it's going to also give us the corresponding sigma 2, the perpendicular stress, or the stress on the perpendicular face. So it's two equations in one. However, we also can look at this part of the equation and we say, oh, that's actually the same piece that we get by plugging in this other angle. That's actually the max shear stress. So this actually looks like one equation. It's actually a sub-equation, but look, we got a plus and a minus, which really is two equations. So this guy here actually has four equations buried into it. We're getting two stresses for the principal stress faces, which means once we rotate the element, these two, sigma 1, sigma 2, and we're getting two values for shear stress, which is just the action-reaction pairs, which basically means, yes, it's just positive and negative. It's really only one value, but it's got both a positive and a negative on the different faces. So the sigma x is giving us either tension on both these faces or compression on both these faces. The sigma y is giving us either tension or compression on both these faces. And the tau is saying, look, I'm going to have it in one direction on one face and the other direction on the other face, and that defines all four faces. So this equation here is really the key to principal stresses, because in it we're going to get both values of the normal stress. So for any rotation, phi, we're going to get an angle rotated at that value. We're going to get the sigma 1, we're going to get the sigma 2, and the tau xy from this equation. This equation gives us those values on that rotated face. This equation gives us what the maximum values are for any rotation. And once again, these two values, which are the principal normal stresses, and these two values, which are the principal shear stresses, do not occur at the same exact angle. We're going to look at that in a minute. Okay? So this equation is really a super equation, because in it we get both maximum normal stresses and both maximum shear stresses. Now if we look at this even further, we notice, oh my gosh, this is even easier than that, because this is just the average stress, this part of the equation. And this over here is the max shear stress. In fact, you'll notice these two terms are nearly identical, because this term and this term are the same except for one stroke. This term is missing that other stroke. It's just got a negative instead of a positive. So this is the average stress, and this is actually the difference of the stresses over 2. And we have the shear stress. See how easy that is? This part is the average stress. This part is actually the shear stress. Okay, now we're actually going to do more with the transformation of stress next lecture. Today we're going to focus more on just understanding those principal stresses. Now, if we go back to an element like this, what we have is some kind of piping element with a whole bunch of stinking forces on the thing, and we can actually evaluate the stresses anywhere. If we want to understand the stresses at H and K, we're going to have to make a section cut through H and K like this. We can then draw our section out here somewhere. We've got H right up here on the element, and we got K right down in here at this point, these 2 points. Now it helps to lay all this out. the rest of our part. Now, if we look at this force by force, let's just go ahead and define some axes. Let's say, well, this is our z-axis to maintain the same nomenclature, and this is our y-axis, and this is our x-axis. So if that's true, we see this F6 is going to give us a stress in the x direction, or let's say it's a force in the x direction, which we're going to turn into a stress, and that's due to 6. And we see that that also is going to give us a moment like this. This is the moment due to 6. Now we've resolved this into all its components here. Now this is going to cause a normal stress on this point, and this is going to cause a normal stress on this point. So the stress at point H is going to be a combination of P, the stress due to this force, axial, and the moment, the MC over I due to this. At this element over here, we see that this is also giving a normal stress, but that this moment is giving nothing. Now if we look at this other force, this looks like F5 is in some wacky direction, so we'd have to turn that into a shear force. This is the force due to 5, and a normal force, this is the force due to 5. In the X, this is the normal force due to 5. In the Z, this normal, we are also going to get a moment. Both of those are going to cause moments, so we're going to get a little component of moment like this, and a little component of, let's see, we're also going to get a little component of moment like this due to 5. And we would have to calculate the shear stresses and the normal stresses, the P over A and the MC over I and the TR over J of all these stresses. Then we take this little force and we see that causes a shear stress, a shear force in this direction, and we see that it also causes a moment, looks like a negative Y moment like this. If we want to understand the stress at these points, we're going to have to resolve, if I redraw this section like this, just draw part of it, we're going to have to resolve it into the total force in the X, which is the summation of all the components from these different pieces, and the sum of moments in the Z, and the sum of moments in the Y, and the sum of forces in the Y, and the sum of forces in the Z, and the sum of forces in the X, and the sum of torques about the X. When we're all done, we're going to get a stress at this point due to the P over A plus MC over I for both components. We're going to get M due to this and an M due to this. And we're going to get shear stresses due to this force acting here, VQ over IT stresses. We're going to have to count for all of that at each of these points. That is actually a little challenging. It's actually not very hard. It's the same stuff we've been doing, but most folks get a little overwhelmed by all the components, as you see here in figure 8.16. As you can see, we've now resolved all of the forces, the F4, 5, and 6 that we cut off, into their equivalents. We have a Px, we have a T, a moment about the X. We have a P in the Y, and we have a moment about the Y. We have a P in the Z, and we have a moment about the Z. At point H, we're going to get normal stresses due to P in the X and moment in the Y and Z. Of course, the moment in the Y is acting about that point, so that's going to cause a zero normal stress. We're also going to get shear stresses. Now the Vy is going to cause a zero stress at that point, but the Vz will cause a shear stress, a maximum shear stress of VQ over I, T, in that spot. And in the same way, at point Z, we're going to get normal stresses and shear stresses. Once we have all the stresses on the little elements, what that means is if we pull out point H, we're going to have a little element lying like this, and when we do the P over A plus MC over I, we're going to get a little stress like this on the thing, and we're going to get a little stress, potentially get a little stress like this, and we're going to get shear stresses that are acting like this or in the opposite direction. And if we pull this little element, we're going to get a little element like this. We're going to get potentially normal stresses and shear stresses. Any of these can be zero or have magnitude. And in order to do that, we're going to have to use systematic applications of P over A plus or minus MC over I about both axes, and we're going to get VQ over IT shear stresses. And we had two different directions. So we would have VZ, right? And so on. Is that all that? Here's looking at it closer at those 2 points. We see once we've resolved that into elements, what we're showing here is on the left in 817A, we're seeing all the forces and moments that cause normal stress or potentially cause normal stress, and all the forces and moments that cause shear stress. If we look at the normal stresses, we see P is going to cause a normal stress in the x direction everywhere. The moment is going to cause a normal stress that's a maximum over here at the left at point K, and it's at its other side, but it's zero along that vertical axis where we have point H. The moment about the Z is going to give us a maximum up at point H, but it's going to give us a zero stress at point K, and so on. Our shear stresses, our Vy will cause zero shear stress at point H, since that's at the top, but it causes a maximum shear stress at point K. And Vz causes a zero shear stress at point K, but a maximum shear stress at point H. The torque is going to cause a uniform stress of TR over J, which is going to be maximum and not unchanging at the extreme fiber going all the way around. So we're going to get shear stresses in our directions, and we're going to get normal stresses. Make sense? So let's think about this just a hair longer. Let's look at point H again. At point H, we're going to have a little element like this. We see that our P is going to give us a component of stress. This is at point H. Our My is going to give us zero because we're right at the centroid. Our Mz is going to give us a little resisting. This is due to Mz. This is due to P. We're going to get two components of stress in that direction. You see that? We're going to have no stress on this face. At least not no normal stress. Now, when we look at our shear stresses, we see that this Vz is going to give us a maximum shear stress like this on that face. But our V in the Y is going to give us zero shear stress on this face here in that direction. Our torque is going to give us another component of shear stress that acts like this. So actually our shear stress on this face is going to be a combination of this Vz and this torque, giving two shear stresses which give us the total value. Our normal stress is going to be caused by the P and the Mz. Now if we look at our other point, point K, we're going to see that our normal stress once again is going to give us a component, and our moment about the Y is going to give us a component. Our shear stress in the Y, VQ over IT, is going to give us a component of shear stress, and our torque will give us a component of shear stress TR over J in the opposite direction. So that's what we see here. Our normal stress at point H and our shear stress at point H will be a combination of all those, and the same thing's true at K. Now we then, having the combined stresses on those elements, we can find out what the stresses are for any rotation of the element by just taking in, for each element, taking our values. taking our sigma x and our tau xy on this H element and then rotating it, we can find the principal stresses, and we can do the same thing at the other point. Okay? Here's a little example. For a state of plane stress, if we want to determine the principal planes, principal stresses, maximum shearing stresses, what we're going to do is take this normal stress sigma x, 50 megapascals. Sigma y is now, that's right, negative 10 megapascals. And our shear stress looks like it's in the positive direction, so that's going to be 40 megapascals. We can just plug that into our equations and calculate those principal angles, the principal stresses, and the maximum shearing stresses. We get the angle of where the normal stress is maximum from this equation, plug and chug. We're going to get the principal stresses on that at that angle for the element at that angle from this equation, plug and chug. And then we can calculate the maximum shearing stresses by just taking the magnitude of the last part of that equation. We can also, if we wanted to, find out what the average is. That's done here, and we find out that our angle is 26 and 116. Got that? So the maximum, the orientation of the element where the stresses are maximum are 26.6 degrees. That gives us the stress on the BC face. Now if we want the stresses on the AB face, then that actually is going to be 90 degrees to that, so we'll just add 90 to the first result and we get the other value. And we can plug our sigma x, sigma y, and tau from the original problem into our principal stress equation. That gives us what the magnitudes are. The max stress is 70 megapascals, the min is negative 30. So when we plug in and find this angle and figure out, when we plug into the principal stress equation, what we're actually getting is the maximum min stresses, and those are the stresses on the two perpendicular faces, BC and AB, as we see in 711b. The shear stress is also given by that equation. We find out it's 50 megapascals on that element, and it's in a different orientation. We can actually plug into that equation that gave us theta as S directly, or just recognize that our shear stress will be 45 degrees from our principal stress, as is shown here. And what we also find is that average stress, remember this is just the average stress, is just the first term in the principal stress equation. Another key piece of information is, remember we said when we rotate this element, we're going to get a rotation of the element that gives us the maximum normal stresses, which will never have shear stress. Remember when we plug into the principal stress equation, we're going to get the maximum principal stresses, which will never have shear stress associated with them by definition. But then we're also going to get a different orientation of the element that's 45 degrees away, where our shear stress is maximum. And that face may or may not have normal stress. How much normal stress does it have? It actually has that average stress. So if you take the average of your original stresses, the 50 megapascals and the 10 megapascals, that will tell you how much normal stress you're going to have on the element when it's rotated in a way that gives you the max shear stress. So the max shear stress is coupled with whatever that average stress is. So if the average stress is 0, like if your two stresses are plus and minus 50, then the average stress would be 0, and that would mean that at the orientation of the element that gives you max shear stress, it has no normal stress on that plane. Got that? Here's a little problem. If we have a little bar, we got this little force. We want the stress at point H. All you got to do is make a section cut, draw a free body diagram, and calculate your equivalent forces on that cut at point H. If you don't do this step, you're going to be really confused and not be able to get anything. If we take a look at point P, we see that P is going to give us a force in the negative Z direction on that plane at point H. we see it's going to give us a moment in the negative x direction on that same plane, on that same section cut. It's also going to give us a torque of the magnitude P times 18 acting on that section cut. We're going to need all three of those in order to calculate the stresses at point H. Before we can evaluate stresses, we need to systematically make a section cut, draw a free body diagram, calculate our equivalent forces on the cut, and then apply our equations for shear bending and torque to figure out what the stresses are at the point we're talking about. This is our approach. Bang, pop, pow, smack. Here is our solution. Now, what we've done is drawn a free body diagram of the upper element and then put the reverse of those. So these are the equivalent forces acting on the remaining piece. We saw we had a shear force from that force that was applied. We got that torque and we got that moment. We talked about all three of these. This first part is calculating the magnitudes. The second part is calculating the stresses. That moment is causing MC over I stresses. That shear stress is going to be 0 on that face, right? But then our torque is giving us a TC over J stress, which is not 0. So taking all those into account, we find that our stress in the X direction is 0, the stress in the Y direction is 884 KSI, and the shear stress is 796 KSI. You're going to want to take your time and study this problem carefully before doing the homework and before moving on. If you can't understand this, actually you all can. If you refuse to take the time to understand this, then you're just going to get in deeper water next lecture when we go into stress transformations. Make sense? Continuing, now that we have the stress on the element, we can calculate the angle of the principal plane and the max stresses. So word of warning, in industry, we rarely calculate what the angle of the principal planes are. We usually just calculate what the principal maximum stresses are, the max and min stresses and the max shear stress, and analyze those. We rarely care what orientation that occurs in, but you need to be able to calculate it. And in this class, I'm going to measure whether or not you can figure out where that plane is. Make sense? A word of warning here. So we see here when we calculate our angle of principal planes of where the stresses are, max and min, we found a negative 30. What that means is that angle is down below that horizontal axis. Okay. Here's a little example. I wanted to give you a couple examples of a couple problems that are relatively simple but look tricky. This is just like a problem out of Beer and Johnson. If we have a little plane stress element, which means we have one face that's unloaded, we've got stresses on the other two faces, and let's say with these stresses we want to find the length, what these lengths are, AB and DC. Well, we know AB and DC, if this circle was D, it was 9 inches, then actually those dimensions AB and DC are both 9 inches. However, if we apply a normal stress sigma x, we're going to find that AB is going to lengthen and DC is going to shorten. AB, the lengthening is calculated from Hooke's law, and DC is calculated by accounting for our Poisson's ratio. Now that stress in the Z direction is going to cause DC to lengthen and AB to shorten. So we're going to need to account for all of this if we want to understand what those dimensions are after or during loading. Okay? So we start by calculating our strains, sigma over E and sigma over E. We've got two strains, but we also have Poisson's effect. So our strain in the X direction is our sigma X over E. That's the main strain, right? And then we also have the sigma Y over E and the sigma Z over E, both multiplied by Poisson's ratio and the negative of those. Now we do have a stress in the X direction. We do have a stress in the Z direction. Our stress in the Y direction is 0. We can calculate our strain in the Y direction the same way. We can calculate our strain in the Z direction the same way. Now remember, in the Y direction on this particular part, our stress was 0, but we still get strains from those two other stresses. Once we've carefully calculated all these strains, we now can directly calculate our lengths, remembering that our strain is just the change in length over length. So the change in length BA is going to be this total strain in the X times whatever its original dimension was. This is just a rewrite of the strain equals deflection over original length, delta over D in this case. You see that? This is not hard. It's not intuitive, but it's not hard. Make sure you look at this and understand this. In the same way, we can calculate our other deflection in the other way. If we want the original lengths, we would just add or subtract those deflections from the part. We can also calculate the change in volume by just summing up all those little strains as shown here. That's all I got. Enjoy.